So, welcome, and today we will be starting down with the next version of it. So, while we have studied down a few of the standard techniques for multi-layer perceptron initialization using autoencoders till now, and then we have also stepped into the basic blocks of convolutional neural networks. And till the last class, we have been doing a very simple and the first kind of a convolutional neural network, which was the LeNet, which was available. Now today what we are going to do is something called as a deep CNN, and I would be discussing on the very basic versions of deep convolutional neural networks which came down. And eventually after this, in the next few classes we will be doing our coding exercises which are related to these kind of convolutions. So the first one which I would be starting down is a convolutional autoencoder. So this goes down with the same philosophy as when you had with a fully connected autoencoder, except for the fact that in case of a convolutional autoencoder you have this advantage that we don't have fully connected neurons any further, but now all these connections are convolutional. So that does give us a very distinct advantage over any of the earlier methods in the fact that while in a standard autoencoder where you had all neurons fully connected down, in case of a convolution, because these are convolutional connections going down, so now you pretty much have this comfort available that you can have space invariance as well coming up over there. Now with this distinct advantage coming to play with convolutions over there, there are certain distinct advantages in terms of what mode you can do. So now you can build up on any of the earlier ones of convolutional any of the earlier versions of autoencoder which you have studied, so including stacked sparse denoising autoencoders, and instead of having fully connected neurons over there, you can now have convolutional connections established between the neurons, and this would help you gain down spatial invariance, which is a very important factor, and as well as learn much more compressed and compact representations which can be convolutionally expressed in order to make more meaning coming out of the data. So today without much of a delay, let's get into the topic. So what we would be covering is something of this sort. So initially I would be discussing convolutional autoencoders, and then I would move down to one of the image classification problems with a particular network called as AlexNet, and this is used for solving one of the best problems in the field, and that's called as the ImageNet classification challenge. So ImageNet is basically a challenge where the idea was that you have about 1 million images given down to you, and then there are about 1000 categories in which these images can be divided. So the whole idea was that can we actually divide them like train a classifier in order to do a 1000 class classification problem in the best possible way on these million images. And the next one is a VGGNet, which came down from the visual geometry group at Oxford, and so they just named it as VGG from their own group. So we would be discussing, so these two over there, AlexNet and VGGNet, are some of these early precursors of the most stable kind of architectures which came down in order to solve this problem of classification. So giving you a brief, I would be giving a very brief preview of what the ImageNet challenge was. So starting in so 2017 basically saw the sort of what we call as the ultimate solution of ImageNet. So there isn't any further research and activity going down on ImageNet solutions, because what we felt out in the community is that whatever could be done in terms of understanding images and classifying images has been done. We had to the extent of having like really good convolutional neural networks, really good very deep neural networks, not necessarily only convolutional, which can solve out this problem of ImageNet classification. And subsequently the idea is to move over to even further better kind of ways. So more complicated challenges, say can we identify actions in video, or what today is called as the video activity classification problem or ActivityNet challenge itself. So that's something which is now one of the most predominant driving force within the community and is an active research problem. But nonetheless, since we are doing a classroom level course over here, so until and unless we are done with images, it doesn't make sense for us to even move to videos, though that's also there in the syllabi of this particular course which we are doing. So without much delay, let's get into this one. So a convolutional autoencoder is typically something which is represented like this. So here the idea is that initially you have your inputs given down over here, and the whole objective is that as in a standard autoencoder you would like to reconstruct the same as an output over here. So we are doing the same thing over here, except for the fact that you would see that it's not a perfectly reconstructed output, but there are some blurs and hazy things which come down over here, and that's pretty okay, because if you are just getting the exact one estimate, it does mean that you are at the best of the accuracy, but that also has this risk that you have possibly overtrained and let your network memorize patterns over there. So that is just a given a test of time. So the more you train, the better it becomes over time. The more the data you expose it to, the better validation schemes you have. It works out pretty fine. Now here what comes down is that you have your original image over there, and then the idea is that you will have a set of filter banks, so a set of kernels. And so what we see over here is that 1, 2, 3, 4, 5, 6. So you remember, as in you had for a LeNet where you had just 6 kernels over there, and then you convolve it with this original image, you would get on 6 such outputs coming down. So they are these outputs come down. Now from there you do a subsampling, and this is where you reach down. Now once this subsample layer is present over here, then this part is the fully connected. So as in with the classification problem, as in the LeNet, the objective was that once you went down to the last layer where you had 16 cross 5 cross 5 and you got down 400 neurons over there, then you did a linearization of these 400 neurons, and then these linear neurons were this sort of like 400 cross 1 array of neurons, tensor of neurons was connected down to 120 neurons in the next layer. So here it's almost of a similar thing, except for the fact that over there it was a classification problem. So you connected on 400 to 120, from there to 84, and from there to 10, and then you just had a classification output coming down. But here, since we are interested more of in constructing a autoencoder, so we go down to a lower space, but from there we start expanding up, as in with a fully connected autoencoder. So with a fully connected autoencoder, you just had this input step, you had your hidden layer, and then this output coming down, and you wanted to match this one to that one. Here what goes down more is that once you have these linear neurons available over there, you will try to rearrange them, repack them, and to get down a convolutional volume, such that you can convolve and get down this second other volume, and from there you can again convolve and get down this one. The only difference would be over here to here. So this is an upsampling which you had contra to a downsampling over here, and this step is often called as unpooling operation or a deconvolution operation in itself. So as if you remember clearly, while I was explaining the initial blocks of a convolutional neural network, so I did explain about what is a convolution, what is a pooling operation, what is a subsampling operation, as well as then we went on to another stage where it was called as a deconvolution, and then I made a specific point over there that we will be touching upon deconvolution a bit later on, and that is an interesting stage when it comes down. So now this is the stage when we really need to speak about the deconvolution operator. So here what we do is that you have your input present over here, but then I need to go to this stage, which is an sort of a magnified version of it. So now one way of doing it is trying to do an unpooling. So within that unpooling, the whole logic was so within the unpooling, the whole logic was that you would just be upsampling and replicating it out over there. But then you know that while you are replicating, so if you have a 2 cross 2, you can make it double of the size and make it 4 cross 4. So every single pixel over there, every single location gets replicated to 4. So a 2 by 2 small matrix over there. Now that this replication is happening, so you will be getting down a major problem of what is called as a blocking artifact or a patchy like effect. In order to get down much smoother, one option may be that you can do a bilinear interpolation and solve it out. But instead of that, one way is that you convolve and interpolate it up over there, and that is something which is called as a deconvolution, which we will look in the next step. From here to this image space is again a very standard way. So you just convolve and then get your output over there. There is just one convolution kernel which will be present from going down from these 6 channels onto this one single channel over there, and that is what we can define down the network pretty easily and without any kind of a problem. So deconvolution is where the main challenge comes down. So you see that if you have your sort of a pooling, and then if you would like to do a corresponding thing which is called as an unpooling. So over there how it is related down is that, say I have my 2 cross 2 patch over there, which is also called as a swatch. So and from this patch what I can do is I would like to get down what is my say my resultant pulled out version. So this resultant pulled out version over here is what is called as the pooled map, and now I see that this black patch is what is the resultant of some convolution of this pooling. Okay, now that I got this one for this small 2 cross 2 patch getting represented into a one single pixel location over here. I can also select down what are my variables which actually led to that. So, what this would help me is that when I am doing the other way around, which is going from this smaller version to the bigger version, which happens over here called as unpooling. So, this is my smaller version, from here I am going to the bigger version. So, I know where exactly this had resultant. So, I knew that this black patch actually came from here. So, if I am going to replace it into my unpooled version over there, so I will be putting my black patch exactly at that location instead of going through any other of these places. Now that I have placed this whole thing over there, the major challenge which comes in, that I have some sort of a sparse representation, because the rest of the places I do not know exactly what was there, that was not stored with me. I just had the max pooled out value and the location from where this max pooling was happening, which I can go and replace it back over there in the unpooling time over there. Now, coming with the same logic of a deconvolution, what happens is that in a convolution you have done a weighted sort of a weighted sum, and then you have just replaced it at this location. So, this was a convolution with a stride which was happening. Now, if I want to do a deconvolution, so I will have to have some sort of something called as a fractional stride as well, because if I do a stride of say 1, then I get the same size of an image in a convolution. If I do a stride of 2, I get half the size of the image in a convolution. Now, in the same way, if I do a stride of 0.5, I should be getting down the double of the size over there, but then you cannot technically imagine like what will be a double the stride, and that becomes really problematic. So, the deconvolution block is something which works on that way, which does a fractional slide. So, there has been a new theory, a very recent theory on something which is called as deconvolution. Intuitively, what deconvolution is trying to do over there is that deconvolution is a way of unpooling all of these indices. So, the idea is that using this version over here, if I have multiple of these, so if there are say 4 such unpooled maps or convolutional layers which I can generate out over there, and then shift and translate and freeze them onto this bigger patch, then I should be able to get down a bigger version of the whole image, and that is what comes down and what has been found out from the theory. So, I will put down pointers onto reading down more details over there, except for the fact that deconvolution is not something to be discussed at much of a detail over here. So, when we are trying to I mean at this particular lecture stage basically. So, on a later bit of lecture stage is when we would be much more well versed with how convolutional neural networks are working, how convolutional autoencoders work, and get into transfer learning and computational complexity. At that point of analysis, I would be bringing in back the concept of a deconvolution and actually trying to solve out the whole math concerned around with it. So, for now what you can actually take as a summary just to be done more detailed in later part is that deconvolution is something which solves the opposite of the problem. So, in convolution, if you are convolving and coming down to a lower channel with a lower size, deconvolution is just an other way around, which has a result production which is much more conformal than what we would be getting down with just a nearest neighbor interpolation or a bilinear interpolation. That's the summary and gist of a deconvolution. But then this plays a significant role when you are coming down over here in autoencoders, where you have to go down to a bigger swatch as well. So, this particular blocks do make a very important statement in terms of their criticality of use. So, having done the convolutional autoencoders, the next part is to get down onto what is called as an AlexNet. So, this is a version where so this is the original version of AlexNet as was implemented in 2012 for the paper, which was the first paper with a deep neural network which was able to beat down any of the conventional and classically available models for solving the ImageNet classification challenge. And here as it went down was that you had images which were of a much bigger and a standard size. So, the ImageNet problem itself mandated that all input images to it were 224 cross 224 cross 3. So, they were all color images. The xy dimension was 224 cross 224 as you see over here. Now, what this network was doing is that initially they take down convolution kernels of 11 cross 11, and then they do a stride of 4 and then create out this next version, and there are such 96. So, you would see that there is a 48 bank over here. So, there are 48 layers and there is another similar 148 over here. Now, given the compute requirements and the GPU constraints which they had at that particular point of time, what they decided was that it was not possible to have all 96 kernels evaluated out together. That is why they evaluated out 48 and then 48. It was just for the purpose of memory handling down in a much better way. Now, as in essence, what we would be implementing today, so not exactly in this episode, but in the next lecture we would be doing that. So, today in the terms of contemporary, what we implement these days is that you can put down all 96 ones over here. The next one is 128 and 128, so that becomes 256 kernels. Now, what you see over here is that here the width and height of these convolution kernels is 11 cross 11, whereas in the next layer the convolution kernels become 5 cross 5. Then in the next layer they again become 3 cross 3. In the next layer they become again so they keep on remaining 3 cross 3 and go. Now, if you clearly look over there, there are 5 convolution layers as has been pointed out over here, and then it goes to a fully connected neuron model over there. So, there it connects down to 4096, then again 4096, and from there to 1000 classes, which are for your classification purposes. And this is a 1000 cross 1 hot vector which gets on the output side of it for the purpose of classification. Now, clearly looking at it, if you see, so initially my kernels are quite bigger, they are 11 cross 11, and then subsequently they start becoming half of the size. So, about half of 11 cross 11 is 5.5, or what is the kernel size of 5. Now, about almost half of 5 is 2.5, and that is where they bring in the kernel size of 3. So, this builds up as if a pyramid, which you would typically be building when you are doing a multi-resolution image processing as well. So, AlexNet as such was just a clever way of doing a multi-resolution image pyramid, whereby you do not have convolution kernels which for feature extraction, which are empirically defined, but all of these kernel weights were getting trained on the run as the network was learning itself to classify images. So, my target was to classify image, I was not giving it exactly based on what feature you would be classifying image. Now, as the error backpropagation goes through and you have these weights modifying over here, so what in essence happens is that these weights get modified such that you are now able to classify images in the best possible way, and these kernels would be tuned down to become kernels of a way which help the maximum discrimination between objects of multiple categories, and that is what AlexNet in total is as such. So, you can get through this particular paper, which is available as of now open source, because it was published in NIPS in 2012. So, all NIPS proceedings are pretty much available on the open place, you do not have to worry much about from where to get them, and this is one of the best ways of going through it. So, do make sure of going through AlexNet on this paper, because the assignment problems are not necessarily going to be only from what is there on the slides there. There will be some interesting questions which you would be getting down, for which you might have to go through the paper, and that is possibly the best way of learning deep learning today. So, from the kernels over there, which I had also discussed in earlier as well, showing you this particular image when trying to discuss about deep neural networks and deep CNNs coming down. So, these filters which you see over here, these are basically kernels. Now, few of these kernels do replicate and become like almost Gabor wavelets with a shifted version and rotated version. Some of these become colors, and the reason because in the original one you had a color image. So, you had this R, G and B, 3 different channels corresponding to the whole volume of the kernel, and then each getting visualized in itself. So, some of them are, say over here it is a red blob emphasis filter, this is a green to red edge emphasis filter, this is again a green blob filter, this again becomes a green blob filter. So, they do play a very significant role, and if you look into these kind of filters, a checkerboard kind of a pattern. So, these are very high high frequency filters which come down, and maybe of all the 1000 categories which needed to be classified over there in ImageNet, some of these objects were what needed these kind of very high frequency filters to come into play, and that is why they just got learned. The interesting fact is that they do resemble a lot of these filters which we have designed classically till date, and then that brings in the power of deep learning. So, if you have the whole model defined out pretty fine, and as well you have a cost function which is defined, your experimental data is enough, then you can pretty much, using just the data itself and a cleverly crafted learning rule which we are doing these days, can learn down patterns to extract features from images itself, and that solves a lot of the low level task which we would have otherwise done to solve every single problem. And now the whole art of visual computing comes to a much higher level, much significantly higher level, where you do not need to sit down and handcraft features any further. So, if we go on and try to look into how this was working down, so if you have an input image of a car into this network, then it would convolve, take a rectified linear unit transformation function, then take a convolution, then a ReLU transfer function, then do a pooling, and eventually it would keep on going. Now, as it keeps on going over here, now what you would observe is that it's no more the original form factor of the car which is visible, and then these just start becoming some sort of bit codes, as you see over here, just blacks and whites coming down, and that's something which fires down the neurons and makes it really good to identify with a very high likelihood that it is a car, with a low likelihood, significantly lower second likelihood of it being a truck next to a plane. So, I do not know exactly what it figured out that it said a plane, but the probability is again low, and the whole aspect is that when you are dealing with probabilities and you are just filtering it out. So, even if the dynamic range between them is there, but still the top 5 predictions would just be coming up as it is, though their probabilities are very low, and the network is actually much intelligent in order to say that with a high efficacy it is actually a car, not any of these others. So, there ends up AlexNet, and we can get into the next version, which is called as a VGGNet, and this was a much later on version, comparatively recent, or what you can say, because it came out in 2015, and this whole thing had something interesting. So, if you look over here, there are sort of like banks in which convolution happen. There's so if you look over here, so you have an image of 224 cross 224 cross 3, and then it convolves and gives you 2 channels over there. So, there is one level of convolution which gives you 224 cross 224 cross 64, then again that convolves and gives you 224 cross 224 cross 64. Okay. Now, from there you have your max pooling for the first time coming over here. Now, after this max pooling, it again does 2 convolutions, then does a max pooling, then does 3 convolutions, then does a max pooling, then does 3 convolutions, max pooling, then 3 convolutions, then max pooling, then linearization, and then a final decision coming down over here, and that is how it was working on. So, here you can actually pretty much visualize the structure of the network, and how they put down is that this sort of length of this block along this x direction over here, that is equal to the number of channels present over there, and this is so this is your x direction, this is your y direction, and this is your z direction, or along the z direction is your number of channels. So, as the channels keeps on increasing, the width over there for each of these blocks increase, and as the height and then so the xy dimensions of the image or the space which keeps on decreasing. So, you see this going. So, this pretty much looks like a pyramid. I mean, hold it vertical and then you would see it, or I mean, tilt your screen or tilt your head, you would be getting down a pyramidal like structure. So, but it becomes really hard from here to understand actually what is the nature of the convolution kernels, whether they took a padding over there, what is the kind of strides which they were taking, and then what is the kind of a max pooling operator, whether it was max pooling or an average pooling, and what was the size of the kernels and the stride of the pooling operator as well. So, let us get into the details, because in this paper it is a very nice way in which they have done. So, they have not just presented one single kind of a network over there, but they have put down multiple variants over there. So, one is a 11 layer network, the next one is also an 11 layer network with a modification called as LRN, local response normalization. So, I will come down to that briefly in the next slide. There is another one which comes with 13 weight layers, then 16 weight layers, and then finally 19 weight layers. Now, weight layers, which when they call over here, so weight layers are basically layers where you have certain number of weights to be learned. Now, with the convolutional neural networks, the weights are only just the convolution kernels which are to be learned. If you do a max pooling, that is not a weighted operation. So, the network does not learn anything new over there. There are no parameters to be updated. So, weight layers are just the tunable parameters if they are present over there. So, here initially they have on this 11 one convolution with a, so this 3 basically means that they have a 3 cross 3 kernel over there. Okay. So, the next one also has a 3 cross 3 kernel over here. The next one B, which has 13 layers, you see that there are 2 such 3 cross 3 convolution kernels, and there are 64 channels in each of them, and this is how this whole thing is defined. And wherever there is a max pooling, it is a max pool, and from the purpose that it was always reducing it to half, and looking more into the code part over there, we did realize. So, when I go into the coding part, I will show you exactly if we import the original architecture proposed by the authors, and how you can from there understand what was the math which was done over there. So, this was a 2 cross 2 pooling which kept on, and eventually the rest of it is the same. So, it just depends on introducing more number of convolutional layers at every layer, and then since these are equal size convolutions of 3 cross 3. So, with a 3 cross 3 kernel, as we have done from the earlier one. So, you know that if you want to have the same size of an output, then you would need a padding of 1 and a stride of 1 over there, and then whatever is the size of the input, the size of the output, xy size of the output is going to remain the same. The number of channels will obviously vary down by the number of channels which you put down in your convolutions over here, and that is the simple trick which it was doing. So, at the same kind of a pyramid level of resolution, you take on more number of features and eventually keep on stacking them. Now, local response normalization as it goes is something of this sort. So, the whole idea is that over a window length of n. So, say I have some capital N number of channels as over here. Okay. So, initially on my first input I had a 3 channel input. So, it was 2 to 4 cross 2 to 4 cross 3. Okay. The next one it goes down and makes it 64 channels. So, convolution of 3 cross 3 and 64 channels. Okay. Now, the output over there of 64 channels where you have 2 to 4 cross 2 to 4 cross 64, which is the output of the first after the first convolution on any of the variants A, B, C, D. Okay. Now, there I have these 64 channels present over there. If I look at one particular location over there and say this location is my x comma y location, okay, and I look into my jth channel. Now, I would like to normalize the response of that one in total. So, what this would mean is that if one of these channels cannot suddenly be abruptly high or abruptly low as compared to its neighbors. So, now I would have to have some sort of a moving window which operates on a per pixel basis across the length of the channel, and that is this local response normalization, which prohibits any sudden change along the channels at a given pixel location. So, one is that you are convolving in the xy space. So, your xy ways of changes are pretty much limited. You will not be getting out noisy patterns, but then I do not even want noisy patterns along my channel dimension, and for that I would be putting in local response normalization. This does have a very significant role in case of VGGNet to bring down all responses onto a conformal dynamic range in which it works out. So, as we keep on doing the exercises, you will see and we will explain you how this has an important aspect. And again, like when we try to visualize these kernels, you would be seeing that why this is important to have a local response normalization. And but then it was eventually figured out that this is a too complicated computationally expensive process actually, where you also need to have these factors of alpha and beta, which as of now the authors had just chosen empirically and just put over there, but this k, alpha and beta, these factors are also something critical which can be learnt, and but then their learning is something which again introduces a lot of variability in the system, and eventually down the line people have sort of restricted using local response normalization and have come down with another really interesting concept called as a batch normalization. So, it is not a substitute for local response normalization in any way, but batch normalization is definitely an interesting fact to also go and study. So, one point which these authors had put down and which we also make an important aspect to study is what is the total number of weights, or that is what is called as a parameter space. So, now when these networks start getting bigger and bigger, so you will have a major challenge in terms of fitting them within your available CPU and GPU memory. Now, if the model parameters and weights they just explode out, then you cannot pretty much train them within your network, and if you cannot load your network onto your CPU, then where are you going to do it? So, we need to really calculate out what is the weights, and that will guide me whether I can use, given my hardware of computing, can I use an 11 layer network or can I use a 19 weighted layer network. And the way it is done is, if you remember that if when we were doing down with the fully connected neurons in multilayer perceptron. So, if n number of neurons are connected to m number of neurons and you have one single bias coming over there, then what happens is basically that for each of these, so each of all the n neurons are connected to each of these m neurons, okay, and there is also one bias which goes down over there. So, there is basically n plus 1 cross m is the number of neurons which are connecting. So, now here what you need to do is that if I have convolutional layers, so this is a 3 cross 3 layer and there are 64 such channels, okay. Along with each channel there is also one bias. So, it makes it 3 cross 3 plus 1 into 64. So, 3 cross 3 is 9, 9 plus 1 is 10. So, 10 into 64. So, one of this will have 640 such weights which are to be learned down. So, the next one over here will have 10 into 128 or 1280 weights to be learned. This will have 2560, this will have 2560, these kind of weights to be. Also you need to figure out that over here I had a 3 cross 3, but then my input was a something which was 224 cross 224 cross 3. So that meant my number of weights was 3 cross 3 cross 3. So I have 3 cross 3 in the x direction and y direction, and 3 number of channels in my z direction, which is my color. So this volume total, the number of weights over there is 3 into 3 into 3, and that is 27. Then a bias, which is 28. So this becomes 28 into 64. Now the output over here is 64 channels. So over here whatever kernel goes in, that is 3 cross 3 into 64. So 64 into 9, added to that is a 1 for your bias, and then you have 120 out of those. Now together if you do this total summation, you would be getting down that you have about 133 million parameter, 133 million parameter, not million, I think, yeah, it's 1000. So it's 133,000 parameters which you have over here in this model to learn. The next one is 133,000 parameters to be learned in model B. So this is a whole detailing is where it's given down on the paper. So I would definitely suggest that you go through and do it. We will also have exercises and a bit of solved examples over there when we do the codes. So we will be writing down a network, and then there is a even a sort of a code equivalent way of finding out what is the total number of parameters which we have to, which we can learn down over there. So with that, like we are almost at the end of it with just looking into the performance. So they have been trying to do what is a top 1% and a top 5%, and what is the total amount of error. So the error, as you see, as it goes down with a much deeper network, goes really low. So it's with the top 1%, or the best prediction over there is of a 25.5% error, where, and the top 5% evaluations, the error goes really down to 8% or even lesser than this. So this was the first, like, really early days version of it, and today's networks, much deeper networks, and something which just came out last year, the DenseNet is which beats everybody in the game. So we have those in the next week itself. So there we get to an end, and for more details you can definitely go through the textbook on this particular topic, as well as all the papers which I have been citing down. And then the next class onwards we do more of coding exercises, and there would be a tutorial at the end of it, where we would be solving for any kind of a given network. Then how do we calculate and find out what is the total number of weights and the parameters which we need to do, and how to gauge that number of weights and parameters onto finding out what is the compute requirement which I will have to have, what is the total number of operations or mathematical operations I will have to do in my forward and back propagation, as well as total number of memory which I will be requiring over there, which is critical in terms of understanding your computational limitations given down a particular hardware, that you always don't need to have access to a GPU. Maybe a simpler network can actually work on a CPU, and how to do that. So they will be down a bit at the later part of this week when we have it done. So with that we come to an end with this interesting discussion on some early concepts of deep convolutional neural networks. So stay tuned for the rest of them, and all the best.